Just tell me when to change slides.
Okay, I've got delay here, so I'm gonna mute my audio.
I muted mine.
Yeah, I think. Well, yeah, our audio, I'm not sure what's causing all the audio disturbance.
Yeah, there's a lot of feedback.
It is, right? Yeah, just use this and shut you down.
Is anybody using a computer close to your mic and your speakers? The host? I don't know. I don't think you can hear me.
All right, can everybody hear me okay? We are screen sharing. You know? Yeah.
Still in.
Yeah. Okay, can everybody hear me okay?
Yep.
Okay, and is everybody seeing the first slide there? Technician class license course for alpha antennas and feed lines.
I see it.
Yeah. All right, so. Okay, how do antennas work?
Now that's a video, you know.
No, I don't.
I'll click it.
Uh,
No, back up.
oh, okay.
It normally works. It's this slow.
Okay. Skip.
Yeah. No, thanks. On YouTube. I can't. Come on. Maybe we won't watch it today. This is actually a pretty good video on how antennas actually radiate.
Hmm. Can you play it anyways? Can you play it?
It's
Oh,
No.
but
Yeah,
it's hung up on
Thinking.
something. Well, The whole computer is on that. All right. We'll just maybe come back to it.
Okay. All right, so quarter wave vertical antennas are fairly common, especially for mobile applications. A lot of times they're quarter wave, and then the body of the body of your vehicle actually mirrors the antenna to give you the other half, because you do need a half wavelength. As you can see in that drawing there on the bottom, measures close to 1/4 wavelength, and part of the lesson material later on, you'll find out why it's part of the wavelength. But from one end of the antenna to the other, it can be quite high for longer wavelength frequencies. So like a 40 meter quarter wave antenna is 33 feet high. So if you're doing a vertical antenna, it's a quarter wavelength, 33 feet high, and then the ground mirrors it to give you the other 33 feet. With my in-fed half wave at home, it's a 40 meter in-fed half wave with a matching transformer, 66 feet long. So I've got it stretched out between two trees in my backyard. Very long antenna, but also fairly nice. Typically with quarter wave antennas, you either have to have something to mirror it on the bottom, or you're going to use ground radials. And the input on what constitutes a ground radial, it seems to be, it's one of those things that amongst hams, some people have one belief, some people have others. A lot of people say you have to have 3 radials minimum of 16 or 17 feet or something to that effect. And I've seen videos where people have used multiple, a lot more, like 10 or 12 radials, and keeping them 8 to 10 feet long, and it does just as good. So, but that's the nature of the ham hobby, is experimentation. So people try things that they think might work, and sometimes they do, and sometimes they don't. Half wave dipole antenna. I've actually got an example of one that I built myself. And don't laugh at my gingerbread man, but this is a very specific purpose, because the D-ring holds it up on my rope, because I have a rope that I suspend all my antennas from
Remember, they can't see it.
between the two trees. Yeah. Oh, yeah, the camera's not on. But anyway, that's a 10 meter dipole. And let's see, does it matter which one?
No.
That's a 10 meter dipole. So there is about 8 feet of wire on each side. I suspend the middle from my rope and then pull the 2 edges out. Now, when I use that portably, I just connect a rope to each end of the wire. At home, I hang it on the rope that I've got permanently suspended between the 2 trees on pulleys, so I can lower it down. But that one there, when I go portable, I just tie off a rope on each end right there and then pull it up. I get to use a slingshot as an adult. Slingshot with a weight on it. And
Probably have to stop share in order for them to see the video.
okay.
There may be another way. I don't know how to switch
Okay.
back and forth easy.
All right. Anyway, the half wave dipole measures close to 1/2 wavelength for the selected frequency. And as I said earlier, it can be quite long, because the 40 meter half wave antenna is going to be 66 feet long, roughly. Now, it varies based on how high up you're putting the antenna and what the conditions are, as far as what the ground's made up of, and other aspects. Normally mounted horizontally between 2 vertical supporters, which I like to call trees at my place. And then there are this particular antenna I have never seen before, and it's called a halo antenna.
It's a dipole folded.
Okay. And where is the feed point on it?
In here.
Okay, all right. And we advanced, right?
Yeah,
So-
it's previous. Previous.
Previous. All
You
right,
take that dipole and you just fold it around in a circle
okay.
and it's,
Oh, okay, so the
there's a
feed,
gap here.
all right, yeah. Okay,
So
so
what exactly
anyway,
is a dipole?
um, it was my understanding earlier on that a dipole has two sides, but I have heard people refer to an end-fed half wave as a dipole. But I've always wondered that myself. As far as I know, a dipole has two different sides, and the feed point is in here, and then these wrap around like that, so there's a gap there. Oh, you can't see it. There's a gap right here. Can you see my mouse pointer?
No,
Okay.
Yeah.
How can I make a?
Next to the one.
One season was it?
Next-
Oh, if you see,
1-3.
Okay.
And then you can draw.
all right,
Just gotta
so I
turn it
can
back
draw.
off.
Right. So right here, you'll see that it says there's a 1 3/16 inch gap between this part of the antenna and this part of the antenna. And this is a non-conductive source, I would guess,
PVC.
PVC. So this is one half of your dipole. It's connected in the middle, and then this is the other half of the dipole, and this would be how you feed it back into the. This here goes back into the.
Right.
Okay. So,
We won't talk about that kind of feed point at this.
yeah, this is probably an extra class feed point type setup,
What's that made of? Is that just copper wire?
It's copper tubing.
copper tubing.
You can make one,
Yeah.
yeah,
Like 1/8 tubing?
or half inch. Soft tubing
Yeah.
is easier to work with than
Okay.
your regular copper hard.
Um, I use 1/4 inch tubing for make my coolers for my beer.
And where is that
It's-
suspended?
That I would guess that's a handheld.
Oh.
I
But
mean,
you know, you can put up on a mast,
using this, you'd have to
right, just clamp it to.
figure out some sort of,
Right.
yeah.
Okay.
But you could use it as a handheld. The difference is this is pretty much omnidirectional,
Mm-hmm.
where your normal horizontal half-wave dipole is going to be directional broadside to the antenna. So it takes up less space and it's omnidirectional.
Okay.
And if it's square, they call it a squallow.
And where those connections are, the 2-inch piece and the 5-inch piece, is there a measurement? Or can that just, that's where it hits?
For the whatever frequency this one was designed for, and I don't know. Those measurements were calculated to give you approximately 50 ohm impedance at the feed point.
All right. So orientation, antennas tend to radiate better in some directions than others, and this is probably one of my issues at home because I have there's a drainage canal behind my house, and there's a electric distribution line back there. So the information that I've gotten is when I set up my antennas for long wire antennas, I need to make them perpendicular as close as I can to perpendicular to the electrical transmission line in order to reduce interference. So perpendicular puts my antenna situated so that it's east and west. It runs east to west. So that determines which direction I'm going to radiate. So broadside to the radiator, when you look at that, when mine's situated east and west, I'm transmitting east and west, so I'm transmitting north and south. And that's probably why that transequatorial hop seems to be so nice to me, because I get stations in Chile and Argentina quite often. And a lot harder to get stations in Europe and be able to understand them. but I get one every now and then. For example, in Kansas, you might want to orient the antenna so that the wire runs north to south. And then that would give you east to west transmission, or it would give you a little edge. A lot of people say that the in-fed halves and the dipoles, even though they're slightly directional, it's not a lot. Some others, like the one right behind you right there, that's a 3-element Yagi Uda, Yagi for short, and that's for a 2 meter. So that's for these right here. That radio. The antenna will then radiate best east and west, meaning that you'll be able to cover most of the US, those lucky people in Kansas. All right, and dipole radiation patterns, you see that the antenna runs down the middle of the donut, and I didn't have my donut this morning. But that's all right, because my wife got up and cooked me breakfast on my way out. But anyway, you can see how your radiation broadside to the antenna is out and away from it. So less radiation off of the ends and most from the sides.
Whereas vertical, you still get a similar one, except it's rotated.
Yeah.
And this is in free space. The closer you get to the ground, the more it
Perfect, yeah.
affects the pattern.
Yeah.
It's no longer a nice symmetrical donut.
Okay.
One of the catchphrases amongst ham radio folks is that the antenna is always a compromise. No matter how much effort you put into it, it's compromised in some way, shape, or form because it's not in free space.
And the saying is, with an antenna, everything affects everything.
Yeah. And I got a story for you about that in this. I tried hanging this up on my wire without removing my 40-meter half-wave in-fed antenna. And I couldn't figure out for the life of me why my readings were just all over the place. But what was happening was there was a little bit of wind, and being right there next to the radiator from the 40-meter antenna, it was coupling with the 40-meter antenna as the wind blew, and it was changing how close it was. It was coupling over, and that screwed up all my readings. So I thought I did something wrong on building it and trashed the first set of wires and cut new wires and redid it. And I got to thinking about that. And not 2 weeks before then, I was asking about building a fan dipole and asked how far apart the radiators needed to be. And I was told different things by different people, but somewhere between 4 and 6 inches apart, the radiators had to be to keep them from coupling with one another. And I said, you know what? I bet that's what's happening. So I took down my in-fed half wave, and it was just as smooth as silk from
Nice.
there, getting it lined up. So anyway, the antenna's polarization is defined to be the orientation of the electric field. Remember, the antenna has two fields, electric and magnetic, and they're 90 degrees out of phase. So what you're looking at is the electric field to determine the polarization. And then you adjust your orientation to get the polarization that you want. This is mostly 2-meter and above issue, and could possibly be 6 meters. 6 meters will use simplex sometimes, or local sometimes. But with your HF frequencies, because you're bouncing off of some level of the ionosphere, it's almost always elliptical. So it doesn't matter what the two ends have as far as antennas. You have people in Europe that use a beam and they point the beam to the US, and I talk to them well, actually a beam and my antenna would be the same orientation, but someone in the US with a vertical could still talk to them even though they're horizontal, because once it bounces off of there, it goes into a tumble and becomes elliptical.
What do you mean beam?
A beam antenna is an antenna that has, most of them are like a Yagi antenna. Do you know what a Yagi is?
Nope.
It's a aluminum tube beam that has elements that are perpendicular to it.
Hang up.
Okay, so it's gonna be coming up in the next slide or in a few slides, I'll put it that way. But you'll get to see a little bit of what it is.
Are you talking about what the old TV antennas look like?
Many outdoor TV antennas are Yagi antennas, yes. But there's the TV antennas are a little bit different because they're trying to receive a multitude of different frequencies rather than just a simple, narrow band. So, all right, now this one here I didn't quite understand.
What is this showing? Linear versus elliptical. Circular is a special case.
Oh, okay,
In
I've
fact,
got
they're
it.
all a special case of
Yeah.
elliptical.
Yeah. Okay, and this is relating to back to the last slide where we said that your electric field is what determines your polarization. And then but circular and elliptical polarization, they're moving more, so it works for all types of antennas. So anyway, all right, so first question of the day, which of the following describes a simple dipole oriented parallel to the Earth's surface?
Bravo.
Horizontally polarized, that sounds right.
Bravo.
All right. And thank you for using phonetics there on the Zoom lesson. In which direction does a half wave antenna radiate the strongest signal? All right. The broadside to the antenna, delta.
Remember the big donut?
Yeah. Okay, antenna types, calculating length, wavelength in meters equals the speed of light in a vacuum divided by the frequency. Speed of light, of course, is annotated in the formula by the lowercase c, and is roughly 300 million meters per second. Bob has been kind enough to put the actual exact speed of light on there. And remember, that's in a vacuum. Within the atmosphere, it's a little slower. But anyway, 300 million meters per second. And when we calculate this, we're going to be looking for megahertz anyway. Remember, we're looking at megahertz. So to make things a little bit easier, since megahertz is 10 to the sixth over, or 10 to the sixth with respect to straight up hertz, we're going to put the 300 million meters into 10 to the 6 also. So 300 times 10 to the 6, and then the frequency in megahertz is at 10 to the 6. So the signal's traveling in bare copper, and this is why I pointed out a little bit earlier when we talked about almost a quarter wavelength or almost a half wavelength, is because the speed of the signal when it's inside the copper wire is only 0.95%. Is only 0.95 of C. So that's
Doesn't matter
95%.
if it's copper wire or iron wire.
I'm sorry?
Doesn't matter what kind of wire.
Yes.
Different mediums will have different speeds. We're using copper here because that tends to be what is most frequently used. And keep in mind that this says bare copper. And I have seen dipole antennas that were made of bare copper, but most, like mine here, have the insulation on the outside of them.
Basically, it's a function of the dielectric around the wire. So in air, that's why it's 0.95. If you put PVC or plastic or something on it, it's a different dielectric constant in addition to the air, so it's slower. It's much slower in coaxial cable because of dielectric. If you put it in we found out recently, water. It goes down to about 0.25, assuming it's insulated from the water.
Yes.
Okay, the length of a dipole antenna is actually about 5% shorter than calculated, and as pointed out, that's because that's with bare copper. If it's got a dielectric of some sort or insulator on the outside of it, it's going to be a little less than that. But what generally happens, you want your antenna to be a little bit long anyway, because when you tune it for your target frequency, you're going to be cutting off a little bit each time. And remember that at higher frequencies, shorter cuts, longer frequencies, a little bit longer cut. But it's always easier to take a little more off than it is to add more back on, as I found out building this.
Wire stretcher.
Actually, you don't need to cut it. You can just fold it back on itself, and there's enough capacitance that it looks like it's a shorter wire. Because you'll always screw up and get it a little too short, and then you gotta make it a little bit longer.
Okay, so therefore, your wavelength is equal to 0.95 times the quantity 300 divided by the frequency in megahertz. And this is one of those situations where the Navy, if they want you to calculate that, they'll show you how it's done. But beyond that, they don't show you anything else. What's that?
Needs to know.
Need to know, yeah.
And that 39.4 is an important constant to remember.
Yes, 39.4 inches in each meter. And that comes up in some of the test questions.
Oh yeah, another question. So the length of the antenna matters?
I'm sorry?
The length of the antenna matters.
Yes.
Yeah.
It's dependent on,
Yeah.
on the frequency you're trying to operate at, or the band. So you wanna try to have your antenna be resonant at the frequency you're trying to receive or transmit on.
Oh, okay.
And how to determine if it's resonance, since I just soldered a massive antenna onto my controller here, so not sure if it works better or worse.
The length of the antenna is more important to your transmitter when you're transmitting. Receivers are less. I mean, if it's long enough, you can receive signals, but it's not going to damage anything if it's not long enough or if it's too long. With respect to your transmitter, though, it's all different. With respect to the transmitter, if it's too long or too short, you can have reflected power come back that can potentially damage. But a lot of the modern transceivers, if they see something they don't like, if they see a tremendous mismatch, they won't even transmit. It'll either severely reduce the power or not let it transmit at all. So yes, the length of the radiator does matter. Haven't been able to show you guys this antenna right here that I built, but the 10 meter, 10 meters is half of that is 5 meters, which is roughly 16 feet. And so half of 16 feet is 8 feet. And so for a dipole, you want 8 feet on one side, 8 feet on the other side. One side is connected to the center conductor, the other side is connected to the shield. And then that gives you your full half wavelength for being able to make your transmitter happy. And then you go through and adjust it. You check your SWR and go through and adjust it, cut off a little bit of each end, because you do want to keep the ends even as close as you can. But you cut a little bit off until you hit that target frequency where you see the line on your analyzer or your VNA dip, so that at the very bottom, it's at the target frequency.
We can do some show and tell.
Oh yes, that's like the transmitter and receiver, I think were like length of a paperclip, since this isn't ham radio, but like a drone thing. So I mean, extend the range, but I'm not sure exactly what it does. That's bad.
I can get all.
I'm sorry, could you say that again, please?
Yes, that's what I kind of just soldered onto like a paperclip sized radiator, probably like a good foot of iron wire, and this is like the receiver is also probably paperclip sized, so it extends the range, but I'm not sure if it does anything bad.
Well, do you know what frequency you're trying to transmit at?
I have no clue what the frequency is.
Oh, well. And then the only, well, without some test instruments, I don't know what to tell you.
What is the radio?
I have no clue. It's like a cheap little circuit board connected to a cheap drum, which I just extended the
There's one
radio
thing
on.
about, there's one thing about antennas. Anything will work. Some things work a lot better than others. I mean, you can hook up to your chain link fence and use it as an antenna and it'll work. Best one in the world.
Yeah, and people have used their people who are in areas of the country that have uh rain gutters on their house. People have used those for antennas too. HOAs do a lot, cause a lot of this experimentation. Yeah,
Good for something.
yeah.
Oh, my goodness.
What's that?
I'm just, I'm just surprised at all the different ways you can go about getting an antenna.
Yeah. Yeah, there's lots of different ways to do it. So anyway, this is some examples of calculating half wavelength. So for 70 centimeters, which is the 440 band, you'll see the half wavelength is 12.6 inches. So when you pick up your, like I'll use a Bofang because they tend to be fairly popular. When you pick up your Bofang and you look at that antenna and it's barely 6.5 inches long, that doesn't necessarily match up to what you're seeing here. And remember that that radio also works for 2 meters, which should be almost 19 inches long for a quarter wavelength. So, yeah. And in 10 meters, that's the antenna here that I brought in as an example to show what I'd have to do the math on that. Half wavelength, it's putting it up there in inches. I'd have to break out my calculator and see what 187.8 inches is. But I'm guessing it's around 8 feet. No, half wavelength, so it'll be around 16 feet. But I'd have to do the math. So those are just some examples of how to figure your wavelength. Wavelength, half wavelength, quarter wavelength. You just remember it once you figure your wavelength, if you're looking for a half, you just divide it by 2. If you're looking for a quarter, you just divide it by 4. So that's an important part of that slide. I would guess that Bob was trying to.
And because there's a question coming up.
Yes. Okay, so what is the approximate length? Does anybody need to go back and take one more look? Okay, so there's your formula. The formula for wavelength. Well, the formula at the top there is half wavelength, and that's divided by 2. But 0.95 times 300 over the frequency in megahertz, and then you want to divide it by 2 to get a half, or divide it by 4 to get a quarter. So keep that in mind. And what is the approximate length in inches of a half wavelength 6-meter dipole antenna?
6 meters is the wavelength of the antenna.
Yeah.
Charlie?
I would think that that is the correct answer, but I can't remember. But an easy way to do this,
Mhm.
if you're not one to remember the formulas, is to remember that if 6 meters is the full wavelength.
Okay.
So if you're looking for a half wavelength, you're looking for 3 meters. And since you know me, since everybody knows me and everybody likes me, just remember that my birthday is on March 28th. Okay, because to convert from meters to inches is multiply meters times 3.28. Very simple for me to remember.
Yeah, you got that one right there.
So 3 meters times 3.28 would give you some figure, and then if you multiply that by 0.95 by your multiplier to get bare copper wire, I think you'll come up with Distractor Charlie.
I think you're right.
Okay, so somebody said Charlie, and that is correct, or somebody said 112. And there's all the math down there if you want to do the complicated math instead of the Dan's birthday math. Yeah, just recently I spent my birthday in I went to San Diego for my birthday because my son and his wife had a baby on my birthday last year. So I went there for the 1 year birthday party.
That's awesome.
My poor wife cannot, her stomach cannot handle pork. And so as a result, we're not trusting of, that's the exact one I've got.
You bet this should work.
Yeah. My wife can't handle pork. So as a result, we can't trust Mexican restaurants because they use a lot of lard in everything. So, and the one that I used to go to when we went there to visit is closed now. But there was one that we used to go to and walk in and tell them the situation, and they would scrub the grill real quick,
Oh,
make sure everything was clean so that she didn't get contaminated. It's not a pretty thing. Anyway, when built, a dipole antenna probably won't be resonant on the frequency you want. And this is because as much as we like to pretend that the formula is accurate and it will get you in the ballpark, it is that accurate. The conditions where you're at, because different density of the ground, like here, because our ground is sandy,
mhm.
you have different conditions to deal with than someone that's in the Rockies. Okay.
Mhm.
So that makes a big difference. So in order to tune the antenna, you need to determine its resonant frequency. And there are multiple different tools that will help you to determine the resonant frequency. Some of the modern radios have all kinds of convenience that the old school hams just didn't have. So it was a lot more difficult for them. But modern radios will usually give you an SWR. So you reduce your power as low as you can reduce it with, and then transmit for a couple of seconds, and it'll tell you what your SWR is. And then you can, it's a roundabout way of getting there. You have to somehow or another determine if you need to make it longer or shorter. But like I say, we always make them long so that we can cut them to shorten them. To decrease the resonant frequency, and this is a test question. To decrease the resonant frequency, you need to lengthen the antenna. This is the part that we don't want to do. To increase the resonant frequency, you need to shorten the antenna. So remember the formula, wavelength is equal to 300 over the frequency in megahertz, right? So the frequency is on the bottom of the equation. So whatever happens to the bottom, what you want the bottom to do, you have to do the opposite on the other side. So the other side is the wavelength. If you want the frequency to increase, you have to make the wavelength shorter. You have to make the wavelength go down. higher frequencies, shorter wavelength. The final length will depend on the height of the antenna, trees or buildings or anything metal that it could possibly couple to. All those things are important. So I tuned this one to be it's 1.1 to 1 in my backyard at 17 feet. When I take it to the park and I put it up and it's only 12 feet up with different ground, different surrounding buildings and everything like that, it could be off a little bit. So I may have to tune it some more, or it may make it better. But 1.1 to 1 is pretty good. That was my last cut, was a 1/4 inch off of each end.
Mm,
So and that put me, and actually that put me at 1.1 to 1 at 28.6 megahertz. So pretty happy with that.
mhm.
The final length will depend on the height of the antenna and any trees or buildings, other items nearby. So which of the following increases the resonant frequency of a dipole antenna? Increases the resonant frequency. Charlie, shorting
Charlie.
it. Yes,
Yeah,
ma'am,
Charlie.
that's correct. So there we are, shortening it. Look at that, they remember something. I'm glad I can, like I say, it's been a long time since I did this, so I'm glad I'm hitting on the key things the way I'm supposed to, and Bob's right here catching the ones that I don't. So what is the approximate length in inches of a 1/4 wave vertical antenna, 1/4 wave vertical, for 146 megahertz?
Delta.
Charlie.
Okay, so 2 meters, 146 is in the 2 meter band. So that means 1 meter will be half a wavelength. And a 1/4 wavelength would be half a meter. Who said Charlie? So Charlie, so there's your, and the math, if you do it out with the frequency, is going to be closer than if you just go with the Dan birthday method. So half a meter, so that would be 39, or well, half of 39.4, which brings you up around 19 inches. So, and don't get hung up also on these test questions. There's going to be one, it's going to be on these types of questions, there's going to be one answer that's close and all the other answers will be off significantly.
Mm.
But there's probably some math that's erroneous math that's done to give them some of those other distractors there.
One thing that almost always there'll be two answers
Mhm.
totally out of the ballpark and two that you have to pick
Mhm.
if you're guessing.
They're similar.
Yeah. Okay, HF antennas can be very, very long, as described earlier about my half wave, my end-fed half wave antenna for 40 meters is 66 feet long. So loading a technique to physically short, the end-fed half wave is generally set up as either a sloper or horizontal antenna. I have heard of people using them in the vertical configuration, but getting 66 feet up into a tree is a challenge, even with your slingshot. But loading, which is a technique to show the antenna, it says here a technique to physically shorten the antenna. So it makes it possible to use a short antenna for a longer wavelength. And there's an example of one of those right
We'll
there.
show this after this session when he turns the camera on. This is a 40 meter 1/4 wave. hamstick. It's
Okay.
not 33 feet long,
Yeah, remember, my half wave is 66 feet long.
about 8 feet,
So,
but you see it's wrapped.
So what
That's
makes
all-
a half wave so different from a full?
Half wave is what has been determined to be the best, the best length to be able to transmit, and not have to have, like, half wave for 40 meters is 66 feet. 66, 16 and a half, feet, and you'd have to be at 132 feet if you use the full wavelength. Now, the SWR on a long and on a really, really long antenna may not exactly match up. Right?
Right.
Yeah, so half wavelength is the target. Quarter wavelength can be used, but when you use a quarter wavelength, you do have to have something that mirrors it, like the body of your car or some radials on the ground,
Called a counterpoise,
counterpoise. Um,
sort of a virtual quarter wave,
So
half of the antenna.
right. So I'm going to add to his question and ask about the 5/8 wavelength.
5/8 wavelength. Technically, it has a larger aperture,
Mhm.
which is one of the things I learned in the antenna physics book, which I'm trying to get, which has a lot of equations. But basically, they talk about aperture, which is the effective cross section of the antenna. So obviously, one that's 5/8 long versus quarter wave long has a bigger cross section because it's 5/8 instead of a quarter times the apparent width.
Okay,
So it's basically that aperture or the portion of the radiated pattern. It turns out it's anywhere from 2 to 3 dB better.
okay. Yeah, that's what my dad had in the CB radio days. He had a 5/8 ground plane.
In fact, I think that little one I was using earlier is 5/8.
Oh, okay. Did that answer your question in some way there?
Yeah.
Okay,
Now you can have such things that we won't really talk about in this class as long wire antennas, which are multiple wavelengths long.
yeah. Okay, so loading coils, what are they? Oh, Wolf River. Okay, so one of the popular brands of loading coils is the Wolf River coil, and there are other brands as well. And even Amazon has some. But basically the Wolf River coil is a coil that provides loading to the antenna to make it look like it's longer to your radio. And this radiator on top of it there is usually a the whip part is usually a an extendable antenna. So it's 17 feet long total, but it's several segments that all collapse into one another. So like the radio, the antennas that you used to have on your cell phone at home that you pull up that was 4 or 5 feet long. So it's the same type of antenna, but this one is 17 feet long, and I think the segments are a couple of feet.
There's also a mobile kind of version called the screwdriver.
Yep.
Which does the same thing, except it actually has a motor that moves up and down inside the coil to change where the tap is. So you can change the amount of inductance that you're adding for different bands.
So the drawing doesn't actually show it, but on your Wolf River coil, it's got a slide on it. And so you have every time you change bands, you have to retune it. So you have to take your antenna analyzer over there or plug it in right where you're at to your transmission line, but you do have to walk over to the antenna and slide the adjuster up or down in order to lengthen or shorten the antenna. But they are good antennas. We have at least one person in our club that I know of that uses this antenna for the QRP days when we go out and try to make contacts, distance, long distance contacts on 5 watts, 5 or 10 watts. So they are very effective antennas. And you see at the bottom of the drawing there, it's got ground earth or radials. So it's either grounded by way of a stake in the ground, or you just spread out the radials. But it is an effective antenna. And it's also very, very portable since the radiator collapses. Which of the following describes a type of antenna loading? Remember, loading is making the antenna appear to be shorter or longer. And let's see, which of the following describes a type. There's 2 types you can use.
Yeah. Capacity.
Alpha,
No. I'm sorry.
alpha.
Alpha.
Alpha, okay, electrically lengthening by inserting inductors in radiating elements. And I probably missed that part. I know when I was giving this lesson to my wife a couple of days ago, my wife and my pit bull like to sit by the couch and learn about radios when I'm practicing the lessons so that I'm not running the lesson here in front of new people completely dry. But anyway, yes, electrically lengthening by inserting inductors in radiating elements. You can also use capacitors, and I think it touched on that earlier, and I forgot to point it out. Capacitance is usually done at the top end, and it doesn't make it very friendly to the wind, so you might not see many of those in Florida. I have seen them.
Capacitor hats, it's usually like a round disc sort of affair. And
Mhm.
it actually does the same thing as inductance in series. It electrically lengthens the antenna. It's still magic to me on how that works.
While this technique does allow you to shorten an antenna, the shortened antenna will not be as efficient. And I brought, if we get a chance to do it, I brought some different lengths of antennas for the handhelds that we can take a look at a little bit later. And I have to be honest with you, last night when I did this test to see if it would work, I was positively staggered at the difference. It is significant.
The other effect of a shortened antenna is it narrows the bandwidth. So, that's one of the compromises. You get a shorter antenna. It's not as good efficiency wise, plus it has a much narrower bandwidth.
Okay, and so who was it that asked about the beam antennas a while ago?
Don't ask me to remember names.
Oh, okay. All right, so somebody asked about the beam antennas a few minutes ago, and here's the part on beam antennas. Beam antennas, so I'm going to start a little earlier than this and point out that when you go looking for an antenna and you're looking at the features and benefits of that particular antenna, if it says gain, don't be confused by that. An antenna is a passive device. It doesn't increase power. All it does is take what power is provided to it from the radio and radiate it in the directions that it can be radiated. But beam antennas concentrate the power, all of the power, or most of the power in one direction. So the antenna is said to have gain. That gain is measured in 2 different methods, depending upon how honest the marketing is. If they say dBd, if you look down there at the bottom, it'll say in dBd. That's dB in relation to a dipole, and a dipole is a real antenna that can be measured. It can be viewed. If it says dBi, it's using dBs in respect to isotropic. Now isotropic is a theoretical antenna in free space that none of us have had the privilege of viewing.
It's a point source, so
Yes. So beam antennas generally tend to have higher gain. You've got Yagis, quads, and the world famous dish antenna. And I haven't seen a dish antenna set up for amateur radio, but I'm anxious to see one. Yagis are Yagis can have, okay, like the Yagi that I brought in for an example today has got 3 elements on it. But only one of them is actually connected to the radio. That's called the driven element. And then you've got the other 2 elements. One is called a director and one's called a reflector. The reflector is on the back, the director is on the front in the direction that you would be sending the signal. But it does concentrate the signal in one direction, and antenna gain, and you notice the gain is in parentheses because it's not real gain, it's just gain in a particular direction. Increase in signal strength compared to a reference. And a reference, as I said before, can be either dBs with respect to dipole or dBs with respect to isotropic.
you remember the picture showing the donut?
Mhm.
Okay, that's if you assume you're putting out 100 watts, okay, then you have a certain amount of power on the surface of that donut. If you were to take that donut and kind of separate it and scrunch it around so it all goes in one direction,
Mhm.
that's what happens with the beam antenna.
Mm.
You've still got 100 watts, but now the amount of power per surface area is greater.
Mhm.
There's no actual gain. You're just putting all the power in one direction instead of around that whole donut. That's why they, and it, you know, that's why it's directional, because it's wherever that lobe is pointing, and you get very small amount on the sides and the rear.
Any questions? So here's an example of a Yagi. You've got the 3-element tape measure Yagi, and all these dimensions are specified. There's formulas that you can use, or you just plug it into a calculator on the internet. You can find a Yagi calculator, and it'll tell you where these elements have to be and how long each one has to be, and the distance between each of them. The other part is the coupling right here. This is the middle element. Let's see here. Let me.
Right click, turn your pointer on.
Okay, so the feed point right here in the middle. This is the driven element. That's where your feed point is. This element here is called the reflector. The front element right here, and this is the front direction. So this is your radiation right here, like this. This is called the director. But this is the only one that's actually physically connected to your radio. The other 2 are just providing. Not real sure what they're providing.
Well, the reflector actually reflects part of the signal back so that it winds up in phase and adds, and the director kind of does the same thing in a forward pattern. So the other elements, and you can have multiple directors. But after about 20, it's really diminishing returns, and it also gets kind of long because of the spacing you have to have. The one thing why I put those on there, those are both examples of technician class antennas you can make. for 2 meters or 70 centimeters. And the tape measure is one you actually make from a cheap tape measure. You cut the pieces, and that's a piece of PVC tubing, and it'll fold up.
Yeah.
It's very portable.
And another way, if you're in a windy, if you typically are using this in a windy location, this antenna, this is a popular antenna for doing fox hunts. And a fox hunt is where somebody hides a micro transmitter that's putting out like 0.3 of a watt or so, and you have to locate it. And this is one of the fun things to do is with your club, because pretty much everybody can get in. Anybody that has a handheld can get into it. So this is usually used for a handheld, and another version of this to build, people have used aluminum arrow shafts and use an aluminum like a 3/4 inch or 1 inch square aluminum tubing and make the antenna from that. And then because your arrows are threaded on one end, the end where your point wouldn't typically go, when you put the studs in there, you can unscrew that or screw it back in so that it makes it more portable. You can unscrew the both sides of all three elements and collapse it down. A guy I saw online actually made a bag, so he slides everything in the bag. So he's got his antenna right there anytime he goes out. But anyway, that's a feed point in the middle, and that is the only part that's physically connected to your radio right there. And I brought a jumper so that I could connect it to my radio, and then I forgot to grab my adapters because, of course, the radio has SMAs and all of my cables are 259s. All right. And this antenna here, that's a Yagi also, or is this
So that's a
a
quad.
quad? Okay.
Works like a Yagi. It's slightly less gain and slightly wider bandwidth.
Okay. And these are wires.
Those are wires. You
Okay.
just need some sort of separator, fiberglass pieces or PVC tubing or
Non-conductive.
non-conductive.
Okay.
And they're a full wavelength around the loop. Well, the driven element is. And it's just like the Yagi. The reflector's slightly longer. The directors are slightly shorter. And if you do multiple elements, you calculate them just like you do a Yagi. They get smaller and smaller. as you
Right.
add more. And you can also change the polarization depending on whether you feed it on, say, the bottom or on the side.
Okay.
In one case, it's horizontal, in one case,
okay.
it's vertical.
Yeah.
Where in the Yagi, you just have to rotate the antenna.
Right. And that's when you're using the Yagi handheld, it's real easy to turn it so that it's either vertical or horizontal. Okay, so what is a beam antenna?
Charlie.
Charlie,
Nobody did Bravo?
So, yeah, we actually, that was part of the material. I mean, I said that it was, concentrated in one direction, but I didn't, yeah. And actually, I think it's classified as bidirectional because it does transmit a little bit on the rear, just nowhere near as much. But all right. An antenna that concentrates signals in one direction. I did use that word, I think, too.
Mhm.
Okay,
It's
what is
mostly in one direction.
mostly in one direction? The additional, I'm sorry, what is antenna gain?
Charlie.
Charlie, that sounds good to me.
Yep, Charlie.
Charlie, the increase in signal strength in a specified direction. And I almost made a cardinal error here because as soon as I read increase in signal strength, I said, no, that's not it. and I moved on to the next one, but you gotta read the whole question.
Read the
It's
question
in-
twice and read the answers all the way through before you answer.
Yeah. Okay, which of the following types of antenna provides the greatest gain?
Delta,
I agree. Yes, okay, so 5/8 vertical, 5/8 wave vertical, isotropic, and remember, we said isotropic is theoretical. And it's a measuring pole to measure again, others against the J pole or the Yagi, and I think the Yagi is the correct answer. Very good. All right, so Bob knows I'm a Jeeper, so for some reason or another, he put a duck on here.
Well, I talked about rubber duckies.
yeah.
And I looked it up and that's what I got.
That's
I
it.
did the internet search.
Okay, so handheld VHF and UHF transceivers. So your handy talkie, your handheld, and a lot of people call it a handy talkie because it's called an HT. Technically, I think HT stands for handheld transceiver.
Right.
But okay, so handheld VHF and UHF transceivers, they have very short, sometimes flexible antennas called rubber duck antennas. And they're way short compared to what you need, but they appear longer to the radio through the magic of inductive loading. So you can have a much shorter antenna than a full-size antenna. They are, sorry,
I was gonna say, once again, it's a compromise.
yeah. It is a less efficient antenna than a full-size quarter wavelength. But it works, it gets you out, and it's portable. So it's a lot easier to carry around an antenna with a 6 or 7 inch, or a radio, I'm sorry, with a 6 or 7 inch antenna than it is to carry one around with a 15-inch antenna. In fact, this one here, I closed it up in my center console today.
Part of
because
it's
I wasn't
money
paying
too.
attention.
I mean, if
Yeah,
you buy
part of
a
it is
$20
money.
or $30 Bofang,
Yeah,
and you get a rubber ducky with it. If you put an antenna like I have on mine there, which is close to a quarter wave, it costs as much as that Bofang radio.
yeah,
Right.
yeah. And the old Bofang radio is what I like to refer to as the ham radio gateway drug. That's how I got started. What is a disadvantage of the short flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wave antenna?
Alpha.
alpha,
Alpha is correct. Very good. Compromised antenna, but your let's see, transmits only in circularly polarized antenna. And it says vertically polarized here, but if you turn it sideways, it's horizontally polarized. It is mechanically fragile. And according to this, your rubber ducky,
Is the
this one
most
is
rugged.
not. But yeah, the rubber ducky is pretty solid antenna. But
A
it's
second,
definitely,
is all metal polarized?
I'm sorry.
Is all metal polarized?
It's all metal polarized.
Is all
Uh,
metal polarized?
Is all metal polarized. It depends on its orientation. I mean, as far as an antenna, if it's radiating, it has a polarization pattern. So if the antenna is, remember the polarization of the antenna is dependent upon the electrical.
Current going back and forth.
Yeah,
What direction the current is traveling determines the electric field that's generated.
yeah. So if the elements are parallel to the ground, then that would be horizontally polarized. If the elements, the radiating element is perpendicular to the ground, with respect to Earth, then it would be vertically polarized. So when you're holding your handheld upright so that the antenna is sticking up toward the clouds, you're vertically polarized. And you see some people, they'll turn it sideways when they put it up to their mouth to talk, and that's going to make it horizontally polarized. And all that does, all the polarization does, if you're mismatched, is it's going to reduce the signal considerably. So you may not hear as well.
If you remember from that chart I had last week showing the polarizing filters, and each one that you went through reduced it by half.
Mm.
So when you were 90 degrees apart, you were like a quarter of the signal.
Using a handheld VHF transceiver inside a vehicle is not very efficient because the vehicle's metal frame ends up acting as a shield or a Faraday cage. Signal tends to not be able to get out or not be able to get in. No, that's not why I have the top off the Jeep. I have the top off the Jeep because it's great weather right now. But a lot of people will get a magnetic antenna that they can put on their car, on the outside of their car, and then have the cable go through and then get the appropriate adapter to be able to match it up to their handheld, and your reception as well as your ability to reach out is much greater. Signal strength of transmitted and received signals will be greatly reduced inside your metal cage. What is a disadvantage of using a handheld VHF transceiver with a flexible antenna inside of your vehicle? Reduced due to the shielding effect of the vehicle. Alpha.
Alpha.
Very good. Antenna types, mobile. So an externally mounted antenna, which we just discussed, a magnetic type mount, will work better on a vehicle. 5/8 wavelength vertical antenna is a popular choice. I think the one on your car is a 5/8, right? Or is it half?
So
So you'll notice a difference when you step outside. You'll notice a difference in their both antennas cover, Bob's antenna and the one on my Jeep, they cover the same frequency bands, but his is quite a bit longer than mine.
Mhm.
The quarter wavelength on my Jeep is there because when I go off-road, I didn't want to have to replace the antenna every time I go off-road
Mm.
from it getting whacked against a tree branch or something. Anyway, the 5/8 vertical antenna is a popular choice because it has more gain than a quarter wavelength antenna. And there is a drawing there at the bottom that shows a little bit of,
the radiation pattern
Yeah.
between the two.
yeah,
And you can see because of the different lobes, the 5/8 actually has a stronger signal at a lower elevation angle.
so, yeah, okay, so this is an elevation.
A cross section of the radiation pattern.
Yeah. So this is the ground right here. And you're looking at it through there, as a cross section. So earth down here, sky up, earth down here, sky up here. And then this is your quarter wavelength right there. And it doesn't reach out quite as far. The 5/8, it does have these two lobes right here, but it reaches out much further to the side as well. So 3 dBs further reach than the quarter wavelength.
And it would almost be good for NIVIS
It could,
because of those lobes.
if it will bounce off. All right, let's see. What is the advantage of 5/8 wavelength whip antenna for VHF and UHF mobile service?
Alpha.
Alpha is correct, yes. Has more gain than a quarter wavelength antenna.
It's debatable whether it's 2 or 3, but
Mhm.
somewhere in that range.
And it may have other factors in play too that swing it one direction or the other. Horizontal dipole, okay, here's our takeaways, and I think there's 2 pages of them. Horizontal dipole is horizontally polarized. A half-wave antenna radiates broadside to the wire, to the radiator. Remember, either remember the Dan's birthday method or remember the formula, one or the other. I think this was 2 test questions.
2 test questions out of
Yeah,
everything we've covered.
this is 2 groups. So out of everything we've covered today, 2 of these questions that we covered today will be on your test. So anyway,
Well, actually, it's 2 of what we covered in the next 2 sections.
right. So remember, this is an important figure to remember if you're looking for inches, is 39.4 inches per meter or 3.28 times the meters.
You just round off at 40 also.
Yeah.
Close enough, 40 inches.
And yeah, because like I say, the distractors will be close, but may not be exactly what you're looking for. 0.95 velocity factor. Shortening increases resonant frequency. Quarter wavelength vertical. What is this here?
Toroid. Toroid. Oh, it's a Taurus, but I think
Okay.
it needs a U. I think I
Your
misspelled it.
screen is a touch screen, isn't it?
Yeah. I hate it because
Fancy.
I get too close and messes
Yeah.
up.
Quarter wave vertical radiates horizontal toros. And then, so that's quarter wavelength. So remember, if you're
Horizontal
looking,
donut.
yeah, if you're looking for a quarter, remember that you are, you're gonna divide by 4 rather than 2 for the half. Antenna loading is electrically lengthening
Usually.
through the use of inductors normally. Directional antennas concentrate the signal in one direction, and gain, and with respect to when referring to antennas, gain is your increased signal in a particular direction relative to the reference. Yagi is the most common of the directional antennas.
But they're easier to build.
Yeah. Handheld VHF, UHF rubber duckies are inefficient antennas, but will get you out there. Mobile reduced signal due to car shielding. So when you're in your car, it's better to have an external antenna that you can plug into your handheld or
At least hold it up to the window.
hold it. Yep. 5/8 inch, or I'm sorry, 5/8 wavelength width has more gain than a 1/4 inch antenna. And it says stop recording. So how do I stop
Go to
recording?
more.
More.
Stop.